let's talk about magnetic flux, which is an abstract concept and can be difficult to wrap your mind around it. But I think the easiest way to come to grips with it is to think of it in terms of magnetic field lines. And that's what I've drawn here. I've got these 5 blue arrows pointing down. These represent the magnetic field. And with magnetic fields, the higher the density of the lines, the stronger the field. The lower the density, the weaker the field. So right now, as I said, I've got these 5 lines. But if I take a couple away, okay, now I've got a weaker field. It's a lower density. And so you can see this brown line here, which represents some kind of area or loop or plane you might think of. I've only got 3 field lines passing through it, but with a stronger magnetic field, I've got more field lines passing through it. Now let me talk a little bit about this brown line. As I mentioned, it's a loop or a surface of some sort. We're looking at edge on, so we can't see the area that it encompasses. And although it does have a thickness, ideally it's infinitely thin, so no thickness. So magnetic flux, we want to know specifically how many field lines are passing through this area that is represented by that brown line. So obviously, as I just mentioned, the magnetic field matters. The stronger the magnetic field, the more field lines. Now, another thing that matters is the size of the loop. The smaller the loop, in other words, the less area it has, then the less flux. So the area matters. Another thing that's going to matter is the orientation of the loop to the field. So if I orient it like this, now there's only 4 field lines passing through it. If I continue to change the orientation, 3, 2, until I can come all the way over here, now this has in this orientation, there's no field lines passing through it. Now I know it looks like there's one passing through it. It looks like there's this one field line passing through it. But again, remember I said that this is supposed to be infinitely thin. So in that ideal case, there actually wouldn't be a field line passing through the loop. So we represent the orientation in our formula with cosine of theta. And what is theta? Well, we draw a normal to our surface, and then the angle between that normal and the magnetic field is the angle theta. Now, you may already realize that I have 2 choices for the normal. I drew the one, but I could have drawn this one. How do I know which one to draw? The answer is it's arbitrary. And that could cause a problem if we cared about the flux. We actually don't care about what the flux itself is. We care about how the flux changes, and specifically the magnitude, the absolute value of the change of flux, the rate of change of flux. So even though there's 2 options here for the normal, we don't really care. And the one that we normally pick is the one that makes the flux positive. Now I should mention that the unit for flux is Webers, and we represent Webers with a WB. Capital W, lowercase b, that's the unit for magnetic flux, Webers. Okay, let me back up here. Write that unit down again, because I'm sure I'll reference it. And let's get this back up here. Okay, now I want to talk about Faraday's law. Faraday's law is an extremely important law. And this is the formula for it. What Faraday's law says is that a changing magnetic flux induces a voltage. And that word induce just means creates. So a changing magnetic flux creates a voltage. And in this case, that means that if the flux through this loop is changing, then there's going to be a voltage applied to that loop. And if this loop happens to be a conductor, then there's going to be a current induced. This is how we generate electricity. Most of the electricity generated in the world comes from Faraday's law. Now, some electricity is generated through chemicals. There's some that's generated using solar panels. But I believe it's still the case right now that most of the electricity generated in the world comes from Faraday's law. And that means you've got to change the magnetic flux passing through some kind of loop. And there's three basic ways to do that. You can change the magnetic field, make the magnetic field stronger or weaker. You can change the area. Okay? If you change the area of the loop, that will change the magnetic flux passing through the loop. The other thing you can do is you can rotate the loop. You can change the orientation of the loop relative to the magnetic field. So that's some kind of rotation. And this is what happens in generators. There is rotation that occurs, and the rotation changes the magnetic flux passing through the loops, and consequently a voltage is induced, and that leads to a current because the loops being used are indeed conductors. So this is it. This is magnetic flux, which we have to understand because of Faraday's law. And again, let me just state again, a change in magnetic flux induces a voltage.